Welcome to Lecture 6 of Design of Seismic Resistant RCC Residential Building based on IS 1893 Code 2016. In the previous lecture, we discussed on some major post-analysis checks in ETABs. We discussed there were three major checks to be performed after modeling the structure in ETABs. Those were analysis, log, and results, in which we checked for warning messages and modal instability. We also checked for deformed shape and modal animation. We saw the deformed shape of our structure under the application of various static loads and also earthquake load case. And we compared the observed behavior or observed displacement of our structure with the expected behavior. Now we are left with checking the modal characteristics of the building, and besides checking the modal characteristics, we will also learn how to check for torsional irregularity in our building. First, let me go to my ETABs model. I have already opened my ETABs model here, and if you can remember last time when we analyzed our structure and checked our structure after analysis, we observed some indifferent behavior of the structure. We observed that the deflection and the shear force and the moments in some beams and columns did not appear to be as expected in the general behavior of our structure. So we assumed that there was some error in modeling of our structure. I looked upon this model and found that we had done some errors, and one of the errors was, if you can see, I will select some joints here. We assigned these joints as hinge joints when modeling the staircase, and these hinge joints are giving a different kind of resistance to the structure. These hinge joints are creating a different behavior for the structure. So I selected these joints and assigned no joints or assigned free joint to all of these joints. And we had also modeled hinge joints for these two joints here where the mid landing slab is connected to the column. So this hinge joint is also sort of dividing our columns into two parts, and we are being shown some erratic behavior of columns. So I also selected these joints and made them jointless. That means we did not provide any restraint to these joints also. And another error that we had made was that our diaphragm was not assigned properly. Suppose you can see here we have assigned 3 diaphragms on 3 floors, and there were some double assignment of the diaphragms and they were not assigned properly, so that was also causing the erratic behavior of our structure. So I corrected all the errors in our model. While correcting those errors, I had drawn some secondary beams. I forgot to delete them, so let me just delete these secondary beams first. It is locked, so I will unlock our model and I will select these beams and delete them. Here all secondary beams are deleted here. So after correcting all the errors in our model, I will run the analysis again. Depending on the complexity of our structure, the analysis time taken may be much or less. We saw different kind of solvers present in ETABs under the option Sapphire, options under the assign menu. We had 3 different types of solver there, that each solver was suitable for some particular condition, and based on the complexity of your model, you can choose different solver. So this is our deflected shape. We saw some basic checks. Now first we will see some model results in our ETABs model. Let me go back to my presentation. So let's see first what is modal analysis. Since we are looking at some model results, we are looking at base shear, we are checking the time period of our structure, we are looking at modal participating mass ratios. Before doing all that, let us just understand some brief introduction about modal analysis. So what is modal analysis? Modal analysis, or the mode superposition method, is a linear dynamic response procedure. Since the other name is mode superposition method, this superposition principle is valid only for linear structures. So modal analysis is only valid for linear dynamic response procedure, which evaluates and superimposes free vibration mode shapes to characterize displacement patterns. So what is free vibration and what is mode shapes? Free vibration, as you all know, it is that vibration of our structure in which there is no external force present. We give a certain initial deflected shape to our structure, and then we release our structure from that initial shape, and then our structure will undergo free vibration. And mode shapes mean a mode shape of a structure is the shape of its deflected shape, or we can say a mode shape of a structure is its deflected shape. So modal analysis is used to evaluate and superimpose free vibration mode shape to characterize displacement patterns. Mode shapes describe the configurations into which a structure will naturally displace. If you see on the right hand side, there is a diagram, and we can see different mode shapes of our structure. That means we can see the different configurations into which our structure can displace and have actually displaced. So this is one mode shape. You can say this is another mode shape, this is another mode shape, and this is another mode shape. Mode shapes of lower order mathematical expression tend to provide the greatest contribution to structural response. Among the many different mode shapes of our structure, which depend upon the number of degrees of freedom in our structure, the lower mode shapes usually have the greatest contribution to structural response. As order of the mode shape increases, mode shapes contribute less and are predicted less reliably. So it is easy to truncate analysis when the number of mode shapes is sufficient. In modal analysis, we select only those number of modes up to which our code prescribes. That means we do not select, or we do not study, we do not analyze for all mode shapes of our building. We truncate our analysis, or we complete our analysis at that point up to which that mode shapes is sufficient so that the behavior of the structure can be studied with certainty. We do not analyze, or we do not study for all mode shapes of our structure. A structure with n degrees of freedom will have n corresponding mode shapes. If you remember, our building is a three-story building. We have 3 floor slabs, and each floor slab has 3 degrees of freedom. Since we are defining diaphragm constraint, and we are assuming that our beams are not flexible in its axial direction, there are 3 degrees of freedom for each floor slab. 2 will be translation and 1 will be rotation. So our model, being 3 stories, has 3 into 3 equals to 9 degrees of freedom. So a structure with n degrees of freedom will have n corresponding mode shapes. So modal analysis is a mode superposition method. If you look at this diagram, our final deflected shape of the structure is this, in which the first degree of freedom is displaced to the right side, if we call it first. The second degree of freedom is displaced to the left side, and the third degree of freedom is again displaced to the right side, although in different amount. So this deflected shape is the summation of these 3 deflected shapes. We have superimposed these 3 deflected shapes corresponding to different degrees of freedom, or corresponding to different mode shapes, so that we get this final deflected shape of our structure. So this is modal analysis. If we go to our ETABs model, let us go to our ETABs model. Last time we checked for the deflected shape of our structure and various internal stresses. For those, we used these 2 shortcuts here, or we also went to display. We could go to load deformed shape if we want to see the deformed shape of our structure under different load cases or combinations or different modes of vibration. We could go to force stress diagram and frame peer spandrel link forces to see the diagrams for various internal stresses. Now, if we want to see other results, may it be input results or output results, then we can go to display, show tables, and various options will be available to us. We can see data, we can see tabulated data for different things. We could see for modal definition, in which we can see tabulated data for load patterns, load combination, connectivity of different elements, joint assignment, frame assignment, area assignment. This is from this first modal definition option, we can see tabulated data for various modal. We can also see analysis results. Analysis results pertain to joint output, that output of in various joints that we get from analysis, or outputs of elements or output of the whole structure. And in the finally we can get the design data also. We are yet to perform design, so this won't be needed now. We want to see some analysis results. So from modal analysis, in modal analysis, one thing that we want to check is base shear, time period, and mass participation ratio. So first, to see base shear. What is base shear? Base shear is that equivalent static force which is applied at the base of the building. Base shear corresponds to the earthquake excitation and the hazard level of our area. And in equivalent lateral static force method or our linear static method, that base shear is applied to the base of our building. To get the base shear, go to modal definition column here. First, let me come again. First, go to display, go to show tables. Under this modal definition, expand this form, load pattern definition, expand this tree by clicking on plus sign to the left. Again, click on this load patterns tree by again clicking to the left side, and then click on this table, load pattern definition, auto seismic, IS 1893 2016. So for checking the base shear, go to this option and then click on OK. We will see the base shear for two of our earthquake load cases, that is ELX and ELY. So here are various data relating to the base shear. We just want to go to, here are some of our input information. Suppose our top story, bottom story, period type. This is our time period that we inserted into that form while defining the load pattern. This is our zone factor, site type, importance factor, response reduction factor, and finally in this last column we have our base shear. Our base shear came out to be 271.5672 kilonewton. So in this way we can see the value of base shear in our building. Let me check here. Okay, this ELX and ELY, we get the value of base shear to be 271.5672. And this table you can export to Excel, or you can format, filter, and sort this table here. If we don't need any of this extra information and we just want to see the base shear, you can go to this format, filter, sort option, click on format table, and is visible. Under this column is visible, uncheck all the boxes that you do not want to see. I just want to see the name. I don't want this. I will uncheck all these boxes. I just want this weight used and base shear, and then I will click on OK. So all other columns are removed, and then only this necessary columns is generated. You can also go to File and Export Current Table to Excel. If you want to export this table to Excel, go to File, click on Export Current Table and to Excel. The table that is shown or the table that is generated will be exported to Excel. Our Excel program I have opened here. So this table is exported here. If you want to save this, you can also save this file. I will just click on close. I won't save it, and done. So in this way you can see the value of base shear. Now I want to see from modal properties. To see those modal properties, I will go again to display and show tables, or you can directly click Ctrl plus T key on your keyboard. I'll go to show tables. I don't want to see this base shear data again, so I will unselect this. I'll go to analysis data. Under this analysis results, structure output, expand this, modal information, expand this, and click on modal participating mass ratios. So go to analysis results, structure output, modal information, and table for modal participating mass ratios. On the right hand side, you can choose the load pattern, load cases, and load combinations for which you want to see the information pertaining to this list on the left hand side. I'll just leave these as default for now. I have selected this table for modal participating mass ratios and I will click on OK. Now, what are the things that you need to see here? As you can see, our building has been analyzed for 12 modes: 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Generally, for a residential building, these 12 modes will be sufficient. This third column shows the period of vibration of our structure in that mode. We have, if you can remember, we used our formula from IS 1893 code 0.075 s to the power 0.75 to calculate the time period of our structure, and then we use that time period in our form for earthquake loads while defining load patterns. At that time, during our calculation, our time period came out to be 0.375 seconds. Now if you see, for the first mode of vibration, that is for mode 1, our time period is 0.372 seconds, which is nearly equal to the time period that we calculated. So, and if you see, there are 12 periods or 12 modes of vibration, and for each mode of vibration we have a fundamental natural time period, that is 0.372 for mode 1, and as we go to the other modes our time period decreases. And if you can see, the time period of our first three modes 0.372, 0.331 and 0.298 are spaced closely apart, and then there is a reduction in time period from going to third to fourth mode, and then we have a decreasing time period. So you should also check this. The first 2 or 3 time periods should be spaced very closely apart. Now another check that you need to perform is, what is the modal participating mass ratios? In our modes of vibration, in any particular mode of vibration, what percentage of mass is contributing to that mode or to the displacement in any particular direction in that mode. That is given by Ux and Uy. You see that in our mode 1, the value of our modal participating mass ratios is 64.84% in our first mode, and that is in X direction. So from this, what we can say, our primary mode of displacement or the primary mode of vibration in our building is translation along X direction. Since Ux it is 64.84%, in Uy it is very negligible. So for this says that 65% of our mass contributes to translation in X direction for our primary mode of vibration. And if you see the same thing for second mode of vibration, you see that Ux is very negligible, but Uy is 83.2%. So our primary mode of translation is displacement in Y direction for the second mode. So we see that for the first mode, our primary mode of vibration is displacement or lateral translation in X direction, and for second mode it is lateral translation in Y direction. This is another very important thing that you have to check while analyzing the structure. Our structure should always have primary modes of vibration is translation. That is, for the first and second mode of vibration, we should ascertain that there is no torsion in our building, but rather there are only translations in two orthogonal directions, that is X direction and Y direction. So why is this important? Actually, what is the mode shape of the building? What is the mode shape of a building in mode 1 means the structure finds it easiest to deflect in that pattern. So if we design a structure which finds it easiest to have torsion in itself, then that is not a good feature of the building. Our mode shape is actually the easiest deflected shape that a building tends to attain. And if a building takes it easy, or if a building finds it easy to rotate or to have torsion in itself instead of translating in x or y direction, then that is a bad behavior of our building. So we should make it sure that our primary modes of vibration are translation. And if you can see in the third mode, only 17% is in x direction and only 1% is in y direction. So our third mode is rotation. And from where we can see that, if we just scroll to the right hand side, and for third mode, if we see Rz, value of Rz, that means rotation about Z axis, then we see 62.61%. So our first two modes are translation and our third mode is rotation. So this is a good behavior of our building. So the values in Ux, Uy, Uz, Rx, Ry, Rz represent our modal participating mass ratios. So this is another check to be performed after analyzing the building. Let me go back to my presentation. I have shown the same thing here. To check the time period and modal participating mass ratios, go to Display, Show Tables, Analysis Result, Structure Output, Modal Information, and Modal Participating Mass Ratio. The modal mass participating ratio is a measure of the percentage of the structure mass that participates in a particular mode. It provides a measure of the energy contained within each resonant mode. A mode with a large participating ratio is usually a significant contributor to the dynamic response of a system. In the previous slide, we learned that not all the modes of vibration have equal contribution to the displacement of our structure. Only the lower modes have the significant contribution. As we go higher, as the number of modes is increased, the percentage of contribution is decreased. So we have to see the behavior of our structure in the lower modes of vibration, and we have to make sure that torsion is not a primary displacement response of our building structure. So we saw this in our slide also, in the ETABs model also, the first three time periods are spaced closely apart. And this is the time period of the building in the first mode of vibration and hence in the fundamental natural time period for linear static analysis. So this is the result of modal analysis, and modal analysis is a linear dynamic analysis. In our linear static analysis, the software only gives a result for this first mode of vibration. So for us, only this is our time period, 0.372. So in this check, there is one thing to notice in our code. If you check our 1893 Part 1 2016 code, our Table 6 contains some definitions of irregular buildings and mostly vertical irregularities. Table 5 lists some conditions of plan irregularities, and Table 6 contains some list of vertical irregularities. And vertical irregularities, in number 7 we have irregular modes of oscillation in two principal plan directions. That code or that clause states that let's see from here, in buildings located in seismic zones 4 and 5, it shall be ensured that, this is to ensure that our building or our structure do not have any vertical irregularities. The first three modes together contribute at least 65% mass participation factor in each principal plan direction. That means the summation of mass participation factor in the first three modes should at least be equal to 65%. Let us go back to our ETABs and let us see, we have Ux, Uy, Uz, and some Ux, some Uy, and some Uz gives us the cumulative modal participating mass ratios. If you see that at the end of our third mode of vibration, our cumulative Ux is 0.8248, which is 82%, and sum UY is 84.37%. So both of these are greater than 65%, hence that code clause is satisfied. So the first three modes contribute at least 65% mass participation factor in each principal plan direction is satisfied. And another condition is that the fundamental lateral natural periods of the building in the two principal plan directions are away from each other by at least 10% of the larger value. That means for our first mode of vibration, we will have the largest time period. And for our second mode of vibration, we will have comparatively smaller time period. The difference between those two time periods should be at least or greater than equal to 10% of the larger time period. That is 10% of the time period of our first mode of vibration. So contribution of first three modes, we saw this already. The 65% clause is satisfied. Our natural period of the first vibrational mode, which was a translation, was 0.372 seconds. Our natural period of the second translation mode, which was also translation in another orthogonal direction, it was 0.332 seconds. So 10% is of the larger value of time period. Our larger value is 0.372. Its 10% is 0.0372 seconds. And if we add this difference, if we add this 10% value and we add this time period of the second translation mode, we get this to be 0.3692 second, which is smaller than 0.372 second. So the difference between the time periods of these two translational modes is greater than 10% of the value of larger time period. So our second clause is also satisfied. In satisfying these two clauses, we confirm that according to Codal provisions, our building structure do not have vertical irregularities. This is one of the clauses. We saw in our ETABs model how to see the value of base shear. Now, one of the most important checks that we have to perform in our building is our check for torsion. So, as I discussed in the previous slide, Table 5 and Table 6 of IS 1893 Part 1 2016 discusses some definitions of irregular buildings, and Table 5 discusses about plan irregularities, and Table 6 discusses about vertical irregularities that contribute to torsion in our building. So Clause 7 of 1893 states that the four main desirable attributes of an earthquake-resistant building are robust structural configuration, at least a minimum elastic lateral stiffness, at least a minimum lateral strength, and adequate ductility. These are the four desirable attributes of an earthquake-resistant building, and we are trying to design an earthquake-resistant building here. So Clause 7.1 continues. Buildings with simple regular geometry and uniformly distributed mass and stiffness in plan and in elevation suffer much less damage than buildings with irregular configurations. All efforts shall be made to eliminate irregularities by modifying architectural planning and structural configurations. Our first step to ensuring a regular configuration is always to alter our architectural plans and our architectural elevations. And many of the times that may not be possible. An architect who has designed the building may not express his wish or may not give permission to alter with his plans and elevation. So we have to also see if we can make our building irregular by changing our structural configuration. A building shall be considered to be irregular for the purpose of this standard even if any one of the conditions given in Table 5 and 6 is applicable, that is, conditions for plan and vertical irregularities. There are many lists in this list for plan and vertical irregularities. There are many conditions given on this table, and even if one of the conditions is satisfied among those Table 5 and Table 6, then our building is said to be irregular for the purpose of design using this code. Limits and irregularities for seismic zones 3, 4, and 5 and special requirements are laid out in Tables 5 and 6. So we can see that table in our code and go through those conditions by ourselves also. Now I have posted a screenshot of table 5, definition of irregular buildings plan irregularities for our course here. Table 5 in number 1 talks about torsional irregularity. Since we are checking for torsion, that table number 1 talks about torsional irregularity, and I have used that screenshot here. So usually a well-proportioned building does not twist about its vertical axis when the stiffness distribution of the vertical elements resisting lateral loads is balanced in plan according to the distribution of mass in plan at each story level, and the floor slabs are stiff in their own plane. This happens when plan aspect ratio is less than 3. Our aspect ratio, that is the ratio of length to breadth, is obviously less than 3. So a building is said to be torsionally irregular when, this is important now, a building is torsionally irregular when the maximum horizontal displacement of any floor in the direction of the lateral force at one end of the floor is more than 1.5 times its minimum horizontal displacement at the far end of the same floor in that direction. This means, let's look at the diagram on the left hand side. Suppose our lateral force is acting in this direction. Let's say our lateral force is acting in this direction, then our diaphragm will displace to the same direction in this side. Our diaphragm may be like this initially, and after the application of our lateral force it has displaced in this manner. Now we can see that the displacement on the right hand side is greater than the displacement on the left hand side due to the same force and in the same direction. So if this greater displacement, which is represented by delta max, is greater than 1.5 times the lesser displacement, that is delta min, then our building is said to be torsionally irregular. Remember this, delta max should be greater than 1.5 times delta min for the same lateral force and for the displacement in the same direction. This is one condition. And another condition is that the natural period corresponding to the fundamental torsional mode of oscillation. What is fundamental torsional mode of oscillation? We saw the table for modal participating mass ratios in our previous slide. In that we saw that the first two modes of vibration were translational modes. Translation mode was predominant in the first two modes, and our third mode of that building, or third mode, was the first torsional mode. Our first two modes were translational modes. So our third mode was our first translational mode, and that translational mode, our first translational mode, is called fundamental torsional mode. So the natural period of that fundamental translational mode should be more than those of the first two translational modes of oscillation along each principal direction. So there are two conditions for a building to be torsionally irregular. One is the deflection, the larger deflection is more than 1.5 times the minimum deflection, and the second condition is that the natural period of fundamental torsional mode of oscillation is greater than those of the translational mode of oscillation. Let us go to our ETABs model. I will discard these ink annotations. Let us go for a short period only. We see that first mode is translation in x direction. Our second mode is translation in y direction. Our third mode is rotation. So our first rotational mode of vibration occurs in this third mode. So our third mode is the fundamental rotational mode of oscillation or vibration. And we see that the time period for this fundamental translational mode is less than the time period for both of these fundamental translational modes. Our time period for rotational mode is less than those of translational modes. So our building is not torsionally irregular, or our building is torsionally regular on the basis of this criteria. So we are left with checking the first criteria, that is that displacement criteria. So how do we check for torsion? How do we check for this displacement criteria in ETABs? We have to check this displacement of this our rigid diaphragm at every story. That is, this condition has to be fulfilled in every story. Since we have 3 stories, this condition has to be fulfilled for every story. So first, the general method is we go to a xy plane at a certain story. So in our case, z equals to 2.85 meter is our first story. We go to display deformed shape. We select first earthquake load in x direction load case. We select on the joint and right click on it to show deflection. We calculate the deflection. We see if this condition satisfies or not. And after you can do this, after you have completed the check for first story, you can go to second story and then you can go to third story. First you can complete for earthquake load in x direction load case, and then you can repeat the same process for earthquake load in y direction load case. So how do we do that? Let me just go here. I have already done this. So how do we do that? Let me just go to my ETABs model. I will go to my plan view. First I will go to my first story, that is story 1. This is our story 1. Let me go to the option show deformed shape. First I want to check for earthquake load in x direction, ELX. Apply. So since this is our x direction and we are checking for positive earthquake load in x direction, our earthquake load is being acted upon on this structure in this direction, from left hand side to right hand side. So our structure will displace on the right hand side. And as you can see here, this is our wire shadow which represents the initial undeformed shape of the structure. Now this has deformed and our diaphragm has moved to the right hand side. So we need to find out the deflections of these 2 points, here and here. If you click on this joint, you can see the value here. If you just hover on top of this joint, or you can also click on this joint, you have to right click, and then you see that since under the action of our earthquake load in x direction, our displacement is being deflected or displaced to the right hand side, you have to see the translation in x direction, which is 1.85 meter. And the displacement at the other end, you just go to that joint and right click on it again, and we see that our displacement is 1.191 meter. So you just make note of all these deflections. So our larger deflection will, in this case, will be delta max. Our lesser deflection will be delta mean, and then try to find the relationship between those delta max and delta mean. Similarly, for the same story, for the same story 1, I will check for earthquake load in y direction and I will apply. Now we can see our diaphragm is deflected in the upward direction, in the y direction. So this wire shadow represents our initial position of this diaphragm. This is deflected to the right hand side. So in this case, we will see the deflection of these 2 joints, and for this we will see the translation in y direction because this is under the effect of earthquake load in y direction. So check the deflection of our structure, translation in y direction for both of these 2 joints. The larger will be delta max, the smaller will be delta min, and define or find a relationship between those 2 joints. I did the same for earthquake load x case. For earthquake load x case, I checked for all the 3 floors, floor 1, 2 and 3. Our delta max was 1.849, delta minimum was 1.207. The units are in millimeters. Our second story deflection was this. Our third story deflection were these 2 values. So I just determined 1.5 minimum what it would be. You may or may not derive this column. Let's just find the ratio between delta max and delta minimum. That is this value divided by this value. We get 1.532 for first story, 1.562 for second story, and 1.438 for third story. So what do we see here? Our 2 ratios are greater than 1.5. So delta maximum is greater than 1.5 times delta minimum, and the ratio for this third story is less than 1.5. So based on our first two ratios, our building is torsionally irregular, and based on our third ratio, our building is torsionally regular. So overall, our building is torsionally irregular. This I found under the case of earthquake load X case. I'll return to this again. In the next slide, I determine for earthquake load in Y case. As you can see here, I did the same as in the previous case. For all these three stories, I found X delta max and delta minimum, and I calculated the ratio. In Y direction, all of our ratios came to be less than 1.5. So our building came to be torsionally irregular from this viewpoint. But overall, our building is torsionally irregular based on this 1.5 ratio clause. So what do we do here? Let me go to my previous slide. In this table 5, after the condition for irregularity, what does this code say? Let's look here. In torsionally irregular buildings, when the ratio of maximum horizontal displacement at one end and the minimum horizontal displacement on the other end. First, it says that the ratio of these two horizontal displacements should not be greater than 1.5 for a torsionally irregular structure. But what happens if the ratio is more? There are two conditions. This is the continuation of this table number 5 clause 1. If this ratio is in the range of 1.5 to 2, that means the ratio is greater than 1.5 but less than 2, then the building configuration shall be revised to ensure that the natural period of the fundamental torsional mode of oscillation shall be smaller than those of the first two translational modes along each of the principal plan directions. This we already saw in our previous slide, or we saw in the table for modal participation mass ratios that our time period for fundamental torsional mode was less than our time period for translation in X direction and translation in Y direction. We have adhered to this criteria, and number B says three-dimensional dynamic analysis method shall be adopted. What analysis are we doing now? We are doing three-dimensional static analysis. So for this kind of torsionally irregular structure, we also have to perform dynamic analysis, and dynamic analysis shall be the subject of our next training course. We won't be looking at the dynamic analysis in this training course. And number 2 says if the ratio is greater than 2. So this means 1.5 to 2 seems to be an acceptable range for any torsional irregular buildings. This does not seem to be so much critical. But when the ratio of these two displacement exceeds 2, then there is a problem with the building configuration, and the building configuration shall be revised. So in this way, we can check for torsional irregularity in the building. So these are the primary checks that we performed after the analysis of our structure. I will just come out of this presentation. Our checks end here. We have done the required checks. We can see some other criteria also, which we will discuss in our upcoming lectures. Before wrapping this lecture, I want to talk a bit about our local coordinate axis. I wanted to talk about local coordinate axis in our previous lecture also, but because of time constraint, I was not able to do so. I will just see in a short about local coordinate axis. So for that, I will go to my ETABs model. I will go to 3D view. I will unlock the model and I will click on OK. So let's go to first display. I'll go to assign and clear display of assign, so everything is erased here. The diaphragms are still here, so I will go to display. I'll go to this option here. Here is set display options, the tick mark sign. Now I want to see the local axis or the local coordinate axis, 1 to 3 axis of our beam and column elements. So I will go to object assignments, In object assignment, I will go to frame assignment and then I will click on local axis because I want local axis to be displayed on our interface. After that, I will click on OK, which is at the bottom and hidden here. Okay, our local axes are being shown. We discussed about this global and local coordinate axis in our previous lectures. This that you are seeing here, x, y, z, at the bottom is our global coordinate axis, and this red, blue, green color axis that are shown for each frame element is its local coordinate axis. If we see for any column, suppose let's zoom onto the column here and see this column, we can see that the red axis is along the longitudinal axis of the column. This is the axis 1 for our column. The axis 1 is oriented. The axis 1 in both beam and column is oriented in its longitudinal axis. So this red is the longitudinal axis of our column. The second axis or the green axis or the 2 axis is oriented towards the positive x-axis. This is our direction of our positive x-axis. The green axis represents the 2 axis of this column and is oriented towards the positive x-axis, and the blue axis represents the third axis of this column or the 3 axis and is oriented towards the positive y-axis. Why is this 1, 2, 3 axis important? If we go to our, okay, I have already unlocked the model, so our display frame pair spandrel, this option is not active now. We saw in our previous lecture that there were different internal forces, shear 22, shear 33, moment 22, moment 33, axial force. That 22, 33, 11, whatever be that represents the local axis of our particular frame or same element. And we have to understand which is the primary axis or which is the important axis on which the important internal stresses act. For example, first let's see the local axis of beam we saw for column. I will go to this beam here and let's see the local axis. If I zoom here for this beam, for this beam, let us see that the red axis or the 1 axis is oriented towards its longitudinal axis. So the 1 axis is always directed towards the longitudinal axis of our element, be it beam or column. And the 2 axis here is oriented towards the positive z axis in case of beams, which is the green axis. And 3 axis, which is the blue axis, is oriented in another direction. This you can find the direction of the 3 axis using right hand rule. First determine our 1 and 2 axis, and then you can use your right hand rule to determine the 3 axis. So these are the local coordinate axis of our beams and column. We will see more about this in our upcoming lectures. Our analysis part is complete, and in next lecture we will start with design. We will see the sample design of beam and columns. We will also see the design results generated by our software. We will see the important results that we need, and then we will continue with designing slabs or footings or whatever may be after beams and column. So we will see them. This is the end of our lecture. We will meet again soon. Thank you.